You know, looking at those pictures, it's tempting to believe that the laws that operate up in Skylab are different from the ones that work down here. Well, we all know that's not the case, unfortunately. If we had the same rules operating in different ways in different places, or different rules in different places, life really would get very, very complicated. In science, we try and unify. I think that point's important enough that we ought to take another look at those pictures and see if we can sort out why there is a difference between what we see in Skylab and what we're used to seeing down here on the Earth. And while you look at the pictures, think about Newton's first law. Now, that's the one that says an object moves with constant velocity unless it's acted upon by a force. Now, do you think it's being obeyed? Now that ball's moving at a constant rate and in a straight line. Only when it hits the wall does it appear to experience a force. So, superficially at least, it looks as if Newton's first law is being obeyed in Skylab. Now, if that's the case and it is being obeyed, why does it look so odd? Well, things look odd, obviously, because they're not what we're used to. If you kick a ball down here on Earth, it doesn't go off in a straight line. It goes in a curve. It's constantly being pulled back down towards the Earth by the force of gravity. And gravity's not the only thing that causes a difference between what we see up in Skylab and what we see down here on the Earth. There's another effect. I've got a feather and a hammer. Well, no surprises there. The hammer plummets down and the feather just drifts down to the floor. Well, part of the reason for that is that the hammer is much heavier than the feather. But that's not the whole story. That's the mistake that used to be made a long time ago. The other part of the story is the air resistance. The feather is very light and it's got a large surface area, so it finds it difficult to push the air out of the way. So its motion is badly affected by air resistance. The hammer, on the other hand, is fairly heavy. It's got about the same surface area as the feather, and its motion is hardly affected at all by the air resistance. Well, I hope that convinces you, but I think it's a subtle enough point that we ought to have another look at that experiment, and this time without the complication of the air. That's David Scott. He's going to do the same experiment on the moon. Now, when he does it, they both fall at the same rate. That's not because he's any better at doing the experiment than I am. It's just that the conditions on the moon are different from the ones on the Earth. There's no air on the moon. No air means no air resistance and no complications in the motion. None of the difficulties we had here with the feather and the air resistance. And you know, resistance to motion, and that's just one example of it, is all around us here on the Earth. Here's another example. A coin. And it stops. Again, nothing surprising. It's just friction between the coin and the table. As the coin moves across the table, it rubs. The friction resists the motion, it slows it down. And no matter how hard you look, you're going to find it very difficult to get away from friction, from air resistance, from gravity. All these forces complicate the motion that we see here on the Earth. That's why people like Newton and Galileo found it so hard unraveling the truth. It wasn't the laws themselves were difficult, it's just that they were difficult to see. Well, I keep on going on about how difficult it is to see Newton's laws, so I think it might be nice now if we could demonstrate them fairly directly here on the Earth. And to do that, we'll have to try and get rid of, or at least eliminate as much as possible, the effects of gravity and of friction. Well, gravity's easy. Let's look at the coin. That's not rising, it's not falling. Gravity doesn't appear to be having any effect. That's because it's being counteracted by an upward force from the table. So if we observe motion in a flat plane, this horizontal plane of the table, we can neglect the effects of gravity. That leaves friction, though. How do we get rid of that?
This ice is jolly slippery, as I've discovered twice rather painfully this morning. And of course, that's just another way of saying that the frictional forces are very small. They are in fact small enough for us to demonstrate Newton's three laws very directly. How about this as an example of Newton's first law? Very much like the behavior of that ball in Spacelab, except of course we didn't allow the skater to crash into the wall at the end of the rink. So it's very easy to demonstrate the first law quite directly here. The second law, however, is a bit more complicated. So we are going to clear the ice rink of these skaters and have a look at an experiment that we've specially set up over here. Well, did you recognize that as a demonstration of Newton's second law? We're going to see it again in a minute, but before doing so, let me explain exactly what's happening. Newton's second law relates the force to the mass and the acceleration. To put it concisely, force equals mass multiplied by acceleration. What we did was to apply the same force to both Charles and Linda, and we did that by pulling them with exactly similar elastic bands stretched by exactly the same amount. So the same force in each case means that there's the same product of mass times acceleration. And since Charles is obviously much more massive than Linda is, he's going to accelerate more slowly. Now, in order to make the experiment more quantitative, we weighed Linda and Charles earlier this morning. Charles weighed 11 stone 9 pounds, that's about 73 kilograms weight. And Linda weighed 36.8 kilograms weight. That's almost a ratio of 2 in the weights. And that, of course, means that Charles' mass is almost exactly twice that of Linda. So what would we predict from Newton's second law? Because Charles has twice the mass, his acceleration can only be half as big. So in order to demonstrate this law, we've got to compare the accelerations. But that's a bit tricky. Accelerations aren't very easy to measure directly. However, we can do it indirectly in almost exactly analogous way to the way that you measured accelerations in the experiments associated with this unit. What you did there was to measure both a time and a distance. Now, I hope you remember the equation that relates the time, the distance, and the acceleration. The equation is that the distance traveled is equal to 1/2 multiplied by the acceleration multiplied by the time squared. Note that this is only true for a constant acceleration. So in any fixed time interval, the distance traveled is going to be proportional to the acceleration. And this means that if Linda has twice Charles' acceleration, we'd expect her to move twice as far in any given time. Now, there's one other problem that we've overlooked. That is, we're using an elastic to actually drag our skaters along. And as you know, when I stretch an elastic by a small amount, there's only a smaller force. But if I extend it a large amount, then there's a much larger force. So what happens when our skaters move along is that the force actually decreases. Now, fortunately, we can get around this problem. In the case of a constant force, we can represent the relationship between acceleration, mass, and distance by a graph something like this. This curve shows how Linda would move if the force pulling her stayed constant. But with the elastic, the force gets weaker as she moves along, so she won't travel quite as far in any given time. But for distances of up to 3.5 meters, the difference between the two curves is so small that her acceleration appears constant. The same is true for Charles. So over short distances, we can compare accelerations by comparing the distances traveled. Now, I think our two skaters are ready to try the experiment again, so let's have a look at it a little more closely this time. They started here, and we stopped them here. The distances they travelled are small enough for our constant acceleration approximation. So if we compare the two distances, then it's clear that Linda really has gone twice as far as Charles in that time. Twice the distance means twice the acceleration, just as predicted by Newton's second law. Mind you, we haven't actually proved the second law, because along the way, we've assumed its truth implicitly. We assumed, for example, that mass is proportional to weight. Now, what we've done is to demonstrate that the motion of our skaters it's consistent with the law, if you like. Now, so much for the second law. Let's have a look at the third law. And what I'm going to ask Linda to do is to push Charles across the ice. What do you think is going to happen in this situation? Surprised? Although it was Linda who pushed Charles, she moved off across the ice, and what's more, she moved off a lot faster than Charles did. Let's have a look at that again a bit more carefully this time. Linda's pushing Charles with a force F, so he accelerates to the right. Newton's third law says that the same force F must be pushing back on Linda, so she must accelerate too. But Linda has only half of Charles' mass, so she should have twice his acceleration. That's 2a. Now, while she's pushing, Linda accelerates twice as much as Charles. But when they part company, they both stop accelerating. At this moment, Linda should be moving twice as fast as Charles, which again means that from now on, Linda should go twice as far as Charles in the same time. Well, let's see. Here's where they start. And we'll stop them here. And we'll compare distances like we did before. Well, you can see that that's actually what happens. The distances are in a ratio of 2 to 1, just as predicted by Newton's third law. Well, we've been able to demonstrate all three laws very directly here on the ice rink, just as directly as we could in Spacelab. We just had to take care to minimize the effects of gravity and friction. But of course, Newton's laws are very widely applicable. Can you see how the third law applies in this situation?
It isn't always easy. The New York Times also had problems analysing how a rocket works. They're writing an editorial about Robert Goddard. He was one of the pioneers of rocket travel. And they said about him, "Of course, he only seems to lack the knowledge ladled out daily in high schools." That's pretty strong stuff. And the reason they felt justified in making that remark is that Robert Goddard had dared to suggest that a rocket could travel out from the Earth, out through the atmosphere, and into outer space. It's totally ridiculous, the New York Times thought. After all, a rocket works by pushing back on something. It pushes back, and then by Newton's third law, there's another force pushing the rocket forwards. That's how they thought it worked. Of course, they're completely wrong. They'd misunderstood the whole problem. They might not have got into those difficulties, though, if instead of trying to analyse the problem directly using Newton's laws, they'd use the conservation of momentum instead, an alternative way of looking at the laws. And that's what I'm going to talk about now. And I'm going to use this piece of apparatus here. It's called an air track. And all it offers is a way of getting rid of friction, just like the ice rink, really. It's a V-shaped tube of metal in which there are lots of tiny holes in the side. And air spurts out of these holes, and the gliders ride along on the air. A bit like a hovercraft. Play with this for hours. What I'm going to try and do, though, is explain, using the air track and these two gliders, what I mean by the conservation of momentum. Let's switch it off. I'm going to set up a collision between the two gliders. I'll do it by projecting them along the track using these springs. Okay. What the conservation of momentum says is that if I add the momentum of this one to that, then it's the same before as it is after the collision. The momentum is constant. Would you believe it? I don't think you should really, because I've not really offered you very much evidence. I've just offered you this view. In fact, if I expect you to believe it, I think I ought to do a quantitative experiment. And that's what I'll do. To do a quantitative experiment, I'm going to have to measure the momentum of each of these gliders before and after the collision. Now, momentum is mass times velocity. And I know the mass. This one has twice the mass of that. That's the way they're made. The velocity? Well, I can do that using these devices here. This is just a beam of light. I switch it on, you'll be able to see it. And it comes out from the torch and falls in a photoelectric cell. And then a signal is sent down through the cable to that box of electronics over there. So I'll show you how it works. On this glider, there's a card which is exactly 10 centimeters long. If I push that through the light beam, it'll interrupt it for a known length of time. Here we go. And the velocity comes up on the meter. That's 0.176177 meters per second. Okay, I'll switch off. So, we can measure the velocity of this glider using this device here. And then on the other side, we've got another which is exactly the same, which will measure the velocity of the other glider. So we'll run the experiment through again. Pushing back the springs. Not forgetting to turn on the other light. Okay, we're ready. Here goes. So the momentum of the glider on the left is its mass, 2m, times 0.140. That's 0.280 m. And the one on the right, its mass, m, times 0.237. That's 0.237 m. But because the one on the left is moving in the opposite direction to the one on the right, we need to use a negative sign in front of the momentum there. So add the two momenta together, and the total momentum is 0.043 m. We'll run it on again. Now the momentum of the glider on the left is 2m times the velocity. That's minus 0.107. That's altogether minus 0.214 m. And the one on the right, m times 0.255. That's 0.255 m. So now the total momentum is 0.041 m. Well, I think you'd agree that those two are near enough. And the conservation of momentum applies to any system, any group of objects which are only having forces acting between them. There are no forces coming in from the outside. These two here. But don't go away with the idea that the conservation of momentum is something new. It's not. All it offers is an alternative way of looking at Newton's laws. And that alternative is very often useful when you want to relate the motion before a collision to the motion afterwards. And you don't want to worry too much about what's going on in between.
Well, we started this program off in Skylab, and we implied there that the reason that the motion was simpler than on Earth was because gravitational forces can be neglected. That, we said, was why balls travelled in straight lines rather than in the curved paths that are so characteristic of motion on Earth. But if you think about that for a moment, you might begin to question that assumption. After all, Skylab is only some several hundred kilometres above the Earth. And you must be aware that the force of gravity extends much further than that. It extends all the way out to the moon and beyond, and that's 250,000 miles away. So how can we explain why astronauts appear weightless? And how can we explain why, when they drop an object, it doesn't appear to fall towards the centre of the Earth? Well, I've got a little demonstration to explain that, and it's a demonstration that doesn't mean that I have to risk my leg on the ice rink again. The object I have here, I'll call it a puck, floats around on a cushion of air. It's very similar to the principle of the air track that you've just seen. And of course, the friction is very negligible. You can see hardly any change of velocity as it moves across the table. I'm going to use this puck to try and simulate orbital motion. You can regard this disk in the center of the table as representing the Earth. And what we want to do is to put the puck into orbit around this disk. Now, in order to get this to move around the disk in a circle, I've got to have a force directed in towards the center, a force that will provide a radial acceleration. And I can provide that most easily with a simple spring. If I put the spring to the center of the Earth and connect the other end to my puck, then as long as that spring is extended, it provides a force towards the center, the puck accelerates inwards. Now, in order to get the puck to move around in a circular orbit, I've got to set it off with exactly the right velocity. If I start it off too fast, then you see it takes way off out of the Earth's influence. On the other hand, if I launch it too slowly, then it just careers around and eventually will crash into the Earth. I've got to set it off at exactly the right velocity if it's going to go in a stable circular orbit. Now that takes a bit of practice, but I've been trying for quite a while this morning. There we are, a stable circular orbit. The spring's providing just the right acceleration to bend the path around into a circle. Now, the orbiting puck could represent a screwdriver in orbit, or it could represent an astronaut. It could even represent Skylab itself. Because the acceleration due to gravity is independent of the mass, they all move in the same orbit. So from the astronaut's point of view, a screwdriver will appear to float in the same place. There's nothing holding it in position, so it appears weightless.
We really have been hammering away at Newton's laws, and I think that's fair enough. They've served us very well. One recent illustration of their power has come from the two satellites Voyagers 1 and 2, which explored the outer planets of the solar system. Their paths covered millions of kilometers, and the trips took several years. The paths were calculated precisely, very precisely, just using Newton's ideas. Dramatic confirmation that his laws work, not just on Earth, but out into space.